All right, so like I said, we're going to be covering Chapter 5, and Chapter 5 is entitled, very simply, Gases. And so they spend a lot of time talking about gases and volume and pressure and temperature. So when it comes to gases, in these laws that we're going to cover, you're going to see that there's a relationship between pressure and temperature of all gases, and we do this because that's what we do in refrigeration. In refrigeration, the point is that we remove the heat from a space like we're in here, and we put it somewhere where it doesn't matter that it goes there. Usually residential means in English outside. So we use the refrigerant when it's in the gaseous state to absorb the heat in the room. How does it do that? Well, the refrigerant in that gaseous state, in that vapor state, is flowing through the component we call the evaporator. So we have warm air that's being blown through an evaporator coil, which is much colder than the air in the room. So the target temperature for the air in the room is 75 degrees Fahrenheit. So that return air is usually going to be slightly warmer. So as we blow through a coil, the coil is actually 40 degrees Fahrenheit. There's a heat exchange that occurs in that air. The warm leaves the air and goes into the refrigerant gas, into that vapor as it is boiled off. That's going to boil down to, not to use boil down as a pun, but that's what's going to happen in Chapter 5 where we talk about that. So temperature and pressure. In a system, as the temperature goes up, the gases become less dense, their volume increases, and so therefore the pressure increases. The other thing about a gas is that a gas always takes on the shape of the cylinder that it's in. It exerts force in all directions in the shape of that cylinder. So if it's in this hermetic compressor here, which is filled with gas, the gas volume is shaped like this and is constrained to this. And if it's in the hose here, the pressure is equal all along the hose length. So the pressure always stays the same in all directions. If it's remember the three states of matter we talked about in energy and matter. They were solid, liquid, and vapor, or gas. So when it comes to how much pressure these gases that exert, we take a look at how do the other states of matter exert pressure. Solids is always on what's supporting it. So if I take a brick and I put it on this table, the force of that is going to be on rest on this table right here. In other words, it's weight. It makes sense, right? The weight of it is what it supports. You remove the table, it's going to be whatever it supports next. A liquid, like we have in this bucket over here, we fill it halfway up with water. The force is on what it rests on, but it's also on the sides. That's a liquid. A gas is going to take on the shape of that sealed container that it is in. And the pressure will be equal in all points in there. So, having said that, takes us to, well, how do we measure pressure in refrigeration? And the answer to that is that we use the manifold gauge. It is our go-to basic tool for measuring pressure in a refrigerant system. And I want to talk about this gauge. The first thing is you're going to notice that there are two gauges here. Usually, typically, one gauge is blue, one gauge is red. Blue and red. The blue gauge is used to measure what we call the low pressure side of the system. Air conditioning systems have two sides. They have a low pressure side and they have a high pressure side. Here would be a really good time to say to yourself, why do they have a low pressure side and why do they have a high pressure side? And it would be a really good time for me to explain it. We have a low pressure side because on the low pressure we're absorbing heat. Going back to that energy matter, we're absorbing heat. On the high pressure side, we're not absorbing heat, we're shedding heat. We're getting rid of heat. And we're doing this because we know that certain refrigerants are going to, at different pressures, are going to be better at absorbing and releasing. Absorbing that heat and releasing that heat. So this is why we have a low pressure side and we have a high pressure side. Because we want to monitor that, because then we know how our system is performing. So, manifold gauge, blue gauge, red gauge, low pressure, high pressure. Another thing about the gauge, I made a little drawing of a gauge here, it's not that good. The blue gauge is also called a compound gauge. It's also called a compound gauge. So the blue gauge is called a compound gauge because it reads two pressure readings. The one that you see that starts at 0 and goes 10 pounds, 20 pounds, 30 pounds, 40 pounds, 50, all the way to 500 pounds. When I say pound, I mean pound per square inch. Pound per square inch. So the pound is the pressure, and the square inch refers to the area that that pressure is being exerted on. And then when it comes to gauges, we even add another letter to PSI, pound per square inch. We're going to add the letter G, pound per square inch gauge. And I'm going to explain to you what I mean by that. But before I do that, I said compound gauge, that it reads two pressures. Pound per square inch is a positive pressure, if you will. It is a pressure 0 on a compound gauge means that it's reading atmospheric pressure. Remember, atmospheric pressure is, 14.7 pounds per square inch of force being exerted by the weight of the air over us. So at 0, it's measuring 14.7 pounds per square inch, or you could say it's measuring 1 atmosphere. But what about if we were to remove some of the atmosphere from this space? Then we're starting to read what's called a vacuum. And that's what happens with the compound gauge when you see the needle go below 0. It's no longer measuring pounds of force per area. Now it's reading less than that. And the unit of measure for this is going to be called inches of mercury. Inches of mercury. And it's going to go from 0 inches to 30 inches. And this is when you hear that term, they're vacuuming the system. We're vacuuming the system. We're removing that atmosphere. We're removing the air from a system, a sealed mechanical compression system like you see right here. Why do we do that? Because remember, there's a relationship between pressure and temperature. We're reducing that pressure inside that sealed unit to where we're going to make water boil at way less than 212 degrees Fahrenheit. We're going to make water boil at 70 degrees Fahrenheit. We're going to make water boil at even less than that. So we pull that deep vacuum to remove all of all of that moisture content that's in the system, because an enemy of the refrigeration, air conditioning, mechanical system is moisture. And we want to remove that. So that's why we talk about having a compound gauge, and that's why in a compound gauge, again, remember it means positive pressure increasing above atmospheric pressure, which is measured in pounds per square inch, in this case gauge. And when it's less than atmospheric pressure, when this reads 0, then it's going to be measured in inches of mercury. There's also going to be another device that we're going to use that's going to give us a much more clearer picture of what's going on with that vacuum that we're going to put on. It's called a micrometer. It's a digital electronic device, and it can read down to, generally speaking, 50 microns is the number we use. Once you get to that number, you've dried out your system and it's ready to be charged. So what are some facts so far that we know about this compound gauge? Well, we know, make it simple, we know number one is blue. Now you say, well, that sounds kind of simplistic, but it's part of the EPA exam still. They'll ask you, what color is the low pressure side gauge usually? And the answer is blue. It measures pound per square inch gauge, which means right here, this is 0 PSIG, right here. That means that it's not actually 0. It means that it's actually I'm just going to have to erase something here. Make a little room. It's actually when it reads 0. When that needle's on 0, it's pound per square inch absolute. That's without the G, without the gauge. That says that at 0, it's going to be PSIA, pounds per square inch, absolute. And sometimes we're going to have to know this number because we need it for calculating things like compression ratios. So that will come later. But I want to make sure you realize that this gauge, when at 0, actually means that there's still atmospheric pressure there. When we start to remove atmosphere from a unit, then it will go into a vacuum mode and it will be less than that 14.7. Generally speaking, in mechanics, for doing this, we usually don't get into all these decimal places. We'll just call it 15. It's close enough. Now you'll also see when you look at this gauge that there's a needle, and the outer band points to the pressure. The pressure being PSIG, pound per square inch gauge. But there's inside bands, and they're color coded. They do not measure pressure. What they're telling you is the corresponding temperature for different refrigerants at that pressure. Because different refrigerants have different pressures. Let me see if so, for example, different temperatures with different pressures. On page 75, there's an illustration that's figure 5-5. And they list 3 refrigerants. One is R718. Who can tell me what refrigerant is R718? Go ahead, Juan. Water, right? Remember that I said it's the oldest refrigerant? So at 1 atmosphere, water then and 1 atmosphere at 14.7 pounds per square inch absolute. Water vaporizes, boils at 212 degrees Fahrenheit. But now, how about another refrigerant? This time we'll put up a real refrigerant that you're using, and we'll say R12. We'll go really old school. R12. So at 1 atmosphere, the temperature at the temperature at R12, that refrigerant, changes state from a liquid to a gas. It's not 212. It is negative 20.2. So that's considerably less than it is for water. And we can use these various different refrigerants so that we can remove the heat that's in the room. So now I'm going to talk about the refrigeration cycle, because that's where we're at on page 79. So what you want to do is you want to make notes here and now, and if you're watching this, make notes as well. So the heart of the system is going to be the compressor. So the compressor, drawn as a cylinder, placed at the bottom center of the diagram, is going to be where we create the high pressure and the low pressure side of the systems. So this is where we're going to, rather than say it that way, this is where we're going to create the high pressure for the system. So leaving the compressor, it leaves the compressor as a hot, high pressure gas or vapor. It leaves the compressor as a hot, high pressure vapor. Matter of fact, we have a special word for that. In this case, leaving this, we say that the refrigerant is superheated. So it leaves the compressor through what's called the discharge line. Now from the discharge line, it goes to a device that's going to be used as a heat exchanger. In this case, the heat exchange is going to occur with air. So we're going to take it into a coil. A coil is something that's made up of copper tubing, which refrigerant is inside of, and then it has these coils of fins that help with the heat transfer. And it's going to travel through the condenser, and in the condenser, it's going to get rid of heat. It's going to get rid of all that heat, measured in British thermal units. It gets rid of it because we designed the condenser refrigerant to be hotter than the outside air temperature. Usually 30 degrees, 25 degrees, 20 degrees, depending on the efficiency of the system. But it's always going to be warmer than what we call the ambient air temperature. Ambient air is a baseline thing that you need to know in refrigeration and air conditioning, and it just means the outside air temperature. So it goes through this condenser and it gives off that heat. It gives off all that heat until it gets to the very end of it in this coil. It's serpentine. Serpentine means it goes like this, like a snake, right? Goes like that. It gets to the very end of that condenser, and then where we've removed all the latent heat, that hidden heat that's measured in British thermal units, and then we begin to reduce sensible heat. Now, depending on the design, we're going to say that for this condenser, that it gave off 10 degrees Fahrenheit of sensible heat. Remember, sensible heat. So that temperature intensity is going to be reduced by 10 degrees. That also has a name. It's not called superheat, it's called subcool. And in that subcool state, the matter of refrigerant has gone from being a hot, high-pressure gas or vapor to a less hot, high-pressure liquid. It's changed states completely into a liquid state of matter. And that's occurred here at the end of the condenser. Leaving the condenser in a tubing, copper tubing normally, that we call the liquid line. We call that the liquid line because it's required for a unit to work correctly that the liquid line is a solid column of liquid refrigerant. It travels to another one of those devices, distinguished with a circle and an X. And this is called the metering device. That's called the metering device. The metering device is going to do one thing. Its job is to take that high pressure liquid refrigerant and change it into a low pressure liquid refrigerant. And it's going to do that by creating a choke point in this refrigerant circuit, in this piping circuit. It creates a choke point, and the best illustration of what that looks like is if you had a garden hose and you squeeze the hose and you got to spray. So the pressure behind the hose is high, and then when it gets past that, where it goes out, then it sprays out into the atmosphere where you're watering your yard, right? Greatly reducing the pressure. This is what we do with this. So there's going to be many different types of metering devices we use. Some of them are going to be adjustable. We call those thermostatic expansion valves or automatic expansion valves. Some of them are going to be fixed. Either it's going to be a capillary tube or some sort of fixed orifice that it would go through. And whichever one that it is, they all do the same thing. They reduce the pressure of the refrigerant. So the pressure gets reduced on this side. And one of the things we do when we talk about reduced pressures, remember how I said the manifold gauge is a blue gauge and a red gauge? Well, the blue gauge represents the low side, and so when we draw this, we usually show leaving the metering device this low pressure liquid refrigerant, which is key. It's a low pressure, but it's still a liquid refrigerant. That hasn't changed. There has been no heat exchange that's gone on with this as of yet. It goes into another heat exchanger, typically a little smaller, typically still somehow that serpentine, that snake-like coil of copper tubing with surrounded by fins. F-I-N-S, to help with the heat transfer. And so when it enters into this as far as the refrigerant is concerned, this space, where its volume can increase, it's going to do this. It's going to start to absorb heat as a low pressure refrigerant. As it absorbs heat, it's like it's on the stove, that the refrigerant's on a pot on the stove. We add heat, and what happens? It reacts to that by starting to vaporize, by starting to return to a gas. And all of this liquid refrigerant is going to continue to absorb heat, those BTUs, until we get to the very end of the run in the evaporator. And then we're going to absorb all the heat we can, all the latent heat that we can, and the sensible heat we're going to absorb at that point. So we're going to do the mirror opposite of what we did in the condenser. Over here, we're going to absorb 10 degrees of sensible heat. And that 10 degrees of sensible heat that we absorbed over here, we're also going to call it superheat. Superheated vapor, which means all the liquid has been boiled off. It's now completely a gas, which means that it's safe for it to return to the compressor, because a compressor can only compress gas. An air conditioning refrigeration compressor only compresses gas. And then it leaves here, and this line, this copper line that it leaves, and it makes its return run back to the compressor, is called the suction line. That's the suction line. The suction line, if you look around the room and you see there's one of these, the bigger copper tubing is going to be the suction line, and it's always insulated, because we don't want to absorb heat and start having a flash, a change of state of matter. So that's what occurs here. So it's gas in the compressor, and it's gas out of the compressor. Gas in, gas out. If liquid enters the compressor, it's going to cause the compressor to slug and to break its valves. So any questions about the refrigeration cycle?